There we go. Hi, welcome, folks. Here we are at the Zoom Theater in Danby, New York. And I'd like to say a few words before we start our program for today, which is officially entitled, I See, The Search for Life in Space. All the signs around town, however, put it more succinctly as, Where's the Aliens? And I hope we haven't suckered you into arriving to look at aliens when in fact all you're going to be looking at is rocks floating in space. But I'm sure Zoe's going to do better than that. This is a presentation of the Danby Community Council in Danby, New York. We are just beginning our programs for the year. This is the first one. The second one hasn't yet been scheduled, but if you go to our webpage, which is on the title slide, and that'll show at the end of the presentation as well, danbycc.org. You can always see what we have coming up in mind. We do receive funding from the town of Danby. We get funding usually from the Community Arts Partnership of Tompkins County, from the United Way, and we are also funded by contributions from users, being a computer guy again, contributions from the public. And we do appreciate that whenever someone can give us something back. I am very amazed to learn that we have attendees who are not even from Danby or Tompkins County. This program was originally scheduled for a month ago, and when it unfortunately had to be canceled, I opened the meeting anyway, and there were people from Arizona, from Washington, D.C., North Carolina. Amazing. And we're very happy to see that happen. Having said all of that, and I hope I haven't forgotten anything, yes, by the way, the bathrooms there's one over there, and well, you know where they are in your house. And we will have snacks. Just go to your refrigerator and we'll find them. Well, you'll find them. And Zoe, will you take questions during, or would you rather wait till after? Give us a during or after.
I will have two different times where I'll take questions, kind of an intermission question time and then an ending question time.
Okay, well, that's the important question. If you do have questions, if you're in the Zoom meeting, just raise your hand. We'll spot them on the participant lists. If you're watching on YouTube, it's either too late. Well, it's too late. And with that, we have with us Zoe Learner Ponterio. She's the manager of Cornell Spacecraft. I hope I get this right, Spacecraft Planetary Imaging Facility. The ing part of imaging sometimes appears and sometimes doesn't. And she's given us very interesting programs in the past, and I'm certainly looking forward to this one. What more can I say? Why don't you go on and continue for yourself? Zoe.
All right, thank you very much, Ted. I'm glad to be participating in this program again. Always been a great place with lots of great questions from folks, and I'm excited about the fact that we've got even people coming in from outside of just the Danby community. Yes, is it image or imaging in our name? Used to be imaging, we shifted to image, and so either one is really fine, but technically it is now image, Spacecraft Planetary Image Facility. And we started historically as a place where you could go to look at actual physical prints of images taken by spacecraft. We have negatives. We maintain that archive, but of course we have evolved with the times. We now support research mostly through accessing digital archives of imagery and doing analysis on digital versions using computer software. So that is a lot of what we do on that end as far as interacting with students and researchers. But then we also do what I'm doing today, a lot of community outreach and making sure that all of these images and the discoveries we've made with them get out there to the general public because most of what I talk about is NASA missions, which everything is public domain that comes out of that. There are other space agencies around the world. I don't have control over what they make public, but they do make some things public, and I talk about them as well. So today's talk, as I said, is about alien life. I do not have any pictures of aliens to show you. But what I do have is kind of two talks that I usually do separately that I'm going to put into one today. And that is that when we talk about the search for alien life, there's really two different fronts that it's happening on. One is the search for any life, anything, even if it's a tiny little microbe, just some sign that there is life out there that did not arise on Earth. Then there's the front that's looking for alien life that would be capable of either traveling or at least communicating or at least being detectable over these vast interstellar distances that exist between planetary systems. And so the first one really kind of starts right here in the solar system, so very close by, relatively speaking, and is even now extending out to nearby stars in the form of looking at the atmospheres of planets around other stars to see if we can see any signs, chemical signs of that would suggest life on those planets. The other one kind of starts where that stops and then looks ahead to further stars and even the entire galaxy to think about technologically advanced life. And there the idea, of course, is we know that we would be able to detect us at a certain distance. The idea that if we were the ones out there looking and we were looking back on ourselves, that as long as we weren't too far apart, that our radio signals that we put out just as part of our everyday life would be detectable by someone else. This is pretty much the basis of Carl Sagan's book, Contact, which was made into a movie. I highly recommend both of them. An excellent exploration of that exact concept. So we're going to start out today with talking about the first of those, the search for life, seriously, any kind of sign that there is life out there. And this is a different version. If you have seen a talk similar to this by me in the past, I'm going to be doing things a little differently in that I'm not going to focus so much on past missions and what and how we've learned what we know about these different environments on different worlds. I'm going to focus today on what's currently happening and what's planned in the future as far as this goes, because we really are at a bit of a precipice in our exploration of the solar system, where we have now been spending a few decades establishing the where. Where should we be looking for life? Ultimately, life could exist everywhere. There's certainly places where we didn't think life would exist on Earth, and then we found life there. We still just can't go out looking anywhere, though. So we've found places where we want to narrow our search that are based on life as we know it, at least. And that should not be taken to mean that we don't think that there could be life not as we know it, but you have to start somewhere. So we've got the where down. We've got several targets that you might see in this slide here. So today I want to talk about kind of the what and mostly the how. What are we doing now that we're finally dipping our toe into not just looking for habitable environments, but actually trying to look for evidence of past or current life in those environments. And so the first thing, of course, we do have to answer is, what are we even looking for? So there's the what. We've talked about the where and the how. What about the what? What is it we're looking for? Now, you probably were given a definition of life in a biology class that you took, and you hopefully were told that there is not one set definition that all biologists agree on, let alone a definition that even within astrobiology is agreed upon. Astrobiology is a field that didn't even exist 30 years ago. It's there not because we've found alien life, but it's realizing that we still need people with a biology background who also understand astronomy, who also understand what we might be finding and give us this information of where, what, and how. So that's the job of an astrobiologist. So what I'm going to give you today is a commonly agreed upon astrobiological answer to what is it we are looking for in these other worlds. 4 concepts. First one is that you have to have some sort of contained environment. There has to be a control over the interior and interaction with the exterior, but some sort of encased thing. On Earth, this is the cell. So that's the analogous to Earth life. The second thing that we're looking for is metabolism. And this basically, we think of this as eating, but it's just using something from the exterior, bringing that inside, having chemical reactions that occur that release energy that it can use to do things, whatever that is. Then you have the self-replicating. And this is where things start to get a little debate. It needs to be able to create copies of itself by some sort of internal process. Yes, this is where the idea of viruses come in. Honestly, the second one, viruses could be kicked out on. They don't metabolize. But viruses do, of course, replicate, but they cannot do it on their own. They need to inject their genetic material into a cell, and then the cell does the job of reproducing the virus. We probably all know a lot more about viruses than we knew 2 years ago, but this is where viruses often get kicked out as not living, but there are still some definitions for life that would include them. The key thing is that viruses don't seem to be able to exist without cellular life. And so if we were looking at other worlds, we wouldn't expect to find only viruses, because without cells, they have no way to reproduce. The last one is one that often isn't thought of, and that is that we want to see evolution. We want to see Darwinian natural selection, which means in the copying process, we have to have mistakes that happen on a regular enough basis that those offspring are not exact copies of their parents. This creates variety in the population. And by sheer chance, some of those varieties will do better in the environment than others. And that will lead to them having more offspring, which leads to that trait being dominant. And that is how evolution occurs. We have witnessed this happening over small time scales with simpler life forms, and we see evidence through the fossil record that it's been happening over Earth's entire history. We have decided as astrobiologists that the first 3 are just really interesting organic chemistry, basically. And we really would wait for that 4th one to show that it is a life that can evolve to adapt to different environments. This also is where we bring into the whole past versus current life, in that if a place ever had life, it is possible that even though it might look uninhabitable today, that the life that was there could have evolved to adapt to that environment. We cannot rule that out. We know that Earth has suffered multiple mass extinction events, and yet none of them have ended life on Earth completely. So it is possible to conclude that that is a pretty hard thing to do, that once a planet has life or a world has life, it's very hard to sterilize the whole thing. But ultimately, that is an open question. So now let's get to now we have the what, let's get to the where and also a bit on the how. The first planet I bring up is one that I don't think gets a lot of talk. It's been getting a bit more talk, and that is Venus. And I'm very glad that it's being looked at again. And I think that if anybody knows anything about Venus, they know that the surface is incredibly hot, hotter than the surface of Mercury, that the pressure of the air is crushing like you're at the bottom of Earth's oceans, that the clouds have sulfuric acid in them. Just does not sound like a place you would look for life. And yet, Venus, we now know, probably was once very much more like Earth, and something either gradual or catastrophic happened that vastly changed the surface environment of this planet. What happened is a bit of a mystery, because whatever happened involved basically the entire rocky surface of the planet being remade, which means that there might not be any geological record of that time period before Venus was what it is today, back when maybe it was more habitable. But thankfully, the rocks are not the only thing that preserve the record of a planet. The atmosphere does as well. And so the beautiful thing about planetary scientists is they've been clever enough to run lots of models to show that what happened on Venus a billion years ago, when we think it was once very much like Earth, warmer certainly, but still more Earth-like, possibly with liquid water on the surface, that if that was the case, there could still be signs of that past in today's atmosphere, that the atmosphere did not get destroyed and remade like the surface did. And thankfully, we now are going back to Venus. NASA has selected not one, but two new missions that are being built right now, Da Vinci Plus and Veritas. And actually, the European Space Agency just selected a new Venus mission. The only missions since NASA went with Magellan over 20 years ago have been a European mission called Venus Express and a Japanese mission called Akutsuki. So NASA is finally going back to Venus, and as this picture shows, Da Vinci Plus is a probe with an orbiter, and it's going to descend through the atmosphere very slowly and study that atmosphere in detail and hopefully survive to the surface and give us some surface information as well. But mostly we're hoping to gain information about the atmosphere. Veritas is a complete orbiter mission, so it will stay in space and observe things from there. Now, there are some in-betweens. The surface of Venus, of course, is very hard for a spacecraft to survive on. But up in the atmosphere, there's places where it's not so bad. And so people are already thinking of flying missions to Venus that would never go down to the surface, but could directly observe the atmosphere. So think maybe a balloon-based spacecraft. So Venus is finally getting that attention that I think it deserves. The next stop would be Mars. I'm working our way from inner to outer solar system. So Mars, of course, is the one you've probably heard talked about the most in the idea of looking for extraterrestrial life. And it was actually the first world that we seriously tried to look for life on, and that was with the Viking mission, which included two landers. We see Carl Sagan standing next to a model of them, the Viking 1 and 2 landers that landed in 1976. It's important to keep that date in mind. I'm going to come back to it later. And the idea was we had never landed on Mars. We wanted to land and we wanted to look for life. Now, there had been landings on Mars by the Soviet space program, but this would be NASA's first attempt to have a complex robotics spacecraft land on Mars. We did several experiments to try and determine if there was life in the rocks of Mars. Every single one either came back negative or inconclusive, or one came back positive, but later people came up with a way that it could have been a false positive. And the one thing that we have to keep in mind when we're talking about looking for life is we are still dealing with one data point, one confirmed data point, and that is Earth life, which by all accounts seems to have a single ancestor sometime in the past. That means that concluding there is another form of life out there is an extraordinary claim, and Carl Sagan told us that extraordinary claims require extraordinary evidence. This relates back to Occam's razor, the idea that if you have multiple explanations for something, you really should go with the one that requires the least fanciful explanation, the one that depends most on things that you already are confident in, which means if we can explain something that looks like life by something that's not life, we really should go with the one that's not life. As much as we might want to find aliens, we have to try and avoid the bias of finding what we want to find. And so we must truly rule everything out. So the one positive was determined to be also inconclusive because it could have happened without life. We realized we kind of put the cart before the horse, bit off a bit more than we can chew with this. And there was a lot of disappointment, and we didn't actually go back to the surface of Mars for 20 years for that reason. Now, that doesn't mean that there isn't life on Mars. It just means that this mission wasn't able to detect it because we really did not have the technology you actually need to do an incredibly hard thing of finding life on a completely different world. So we are now, of course, in the era of the Mars rover, no longer landers. And we have established firmly via our wonderful Spirit and Opportunity rovers off here to the side, those are the ones I worked on as a grad student, they answered the question that yes, Mars was once a warmer, wetter world with sustained habitable liquid water on the surface for long periods of time. So that was the established of the basics of the environment as far as air and water and soil. We see off to the right here a model of the Curiosity rover, and that is also what the current Perseverance rover basic framework looks like as well. And Curiosity rover established firmly that there are the ingredients for life on Mars. The organic chemistry necessary for life exists on Mars. Perseverance is taking that final step to actually looking for not just in environmental habitability and raw materials, but also trying to find biosignatures, evidence that there was once life on Mars. Now I get asked, will the rover itself be able to find this? Probably not. I don't like to burst bubbles, but don't hold your breath for that one. I'm not saying it couldn't happen, but this rover is meant to prepare samples to bring back to Earth. It's meant to find rocks that look like they're the most promising to hold biosignatures, signs of past life, to then eventually retrieve and bring back to Earth for full analysis. So Perseverance went to a place that we thought was the best chance of finding these rocks. And it landed in a crater named Jezero next to what we see here, a giant fanned deposit. This is an inflow channel coming into the side of the crater. This was once a crater lake, and that is a delta formation. And that means that delta formation has very well preserved rocks because they formed and then were buried immediately. So well preserved. Wind erosion has exposed them. So we have recently preserved rocks exposed. And also any life would have been preserved there from living in the lake, living on the bottom of the lake, living in the river, living in the rocks upstream. It could have this huge conglomeration of, if there was life at any one of those places, it would be preserved there. And so this is a very similar environment to where we see here's the Mississippi River Delta. And I think we already can see a lot of the similar landforms. So as I said, this rover's main new advance is that it collects samples. And so here we see the first rock that was sampled. We have 2 boreholes into the rock. Each one of those extracted a piece of rock that is about the size of a piece of chalk. And here we see one of those samples inside the drill bit, the coring drill bit that was used to collect it. The rover then carefully puts that into a sealed cached container. And once we build up enough of those, we will drop them onto the surface at a specific location and drive on. Years later, we're not sure exactly when, another mission with another small fetch rover will go back to the surface and will find that sample capsule, pick it up, and take it to a small rocket that will launch off of Mars with those samples and make its way back to Earth. So this is a long game. This is the first step. Again, we might not have definitive answers for a decade or even more on this, but you have to be patient if you want to work in space exploration. And on the subject of returning to Earth with these samples, let's talk about the search for life on Earth. Let's remember this is ongoing. It feels like every time we think that there's an environment on Earth that couldn't possibly be habitable and couldn't possibly have life, we go there, we look, and we find life. And so a classic example of this, if you'll remember, the Viking landers landed in 1976. Only 1 year later, we discovered an entirely new ecosystem on Earth before not thought to be possible. And that was life on the floor of the deep ocean. The first ever expedition to the deep ocean floor was in 1977. So that's a year after Viking and only a year before I was born. So really, honestly, not too long ago, we thought that the bottom of the ocean floor was a life desert, that nothing could survive down there with no access to sunlight. And yet when we went down there, lo and behold, we found a very rich ecosystem. So certain were we that we weren't going to find life that there was not a single biologist on this initial mission. If you'd like to know more about this, there is a James Cameron documentary that was made quite some time ago called Dive to the Edge of Creation. No, I don't think this was Cameron, the other one. Hold on. But this is a National Geographic video that you might be able to find in your library chronicling this. Now, I bring this up because of the discovery of oceans in other worlds, one of which, of course, is Jupiter's moon, Europa. We know for sure that Europa, because of Jupiter's enormous tidal forces on it, it's tugged and squeezed, building up friction in the rocky interior, melting the surface ice into a layer of liquid water that is a salty ocean that we think could be very similar to those deep ocean environments where you could have those volcanic hydrothermal vents at the bottom that would be producing an environment that could sustain life. So what are we doing with this discovery? Well, we are currently building a spacecraft set to launch probably in a few years, I think mid this decade, called Europa Clipper. And this, as you can probably tell by its design, is an orbiter. It's not going to orbit Europa. It's going to orbit Jupiter, but in a very oval orbit that will clip past Europa on several of those orbits, thus the name. And because Europa has no atmosphere, you don't need to worry about the drag or getting too close to the surface. And so the closest pass is currently planned for just 18 miles above the surface. So we're going to get very close to the surface of Europa and get nice up close pictures. But if the interesting part is the ocean inside, what good is it looking at the outside? Well, there are these regions that we call the chaos regions. Most of Europa is a cracked surface, but there are these spots that we think are warm spots. So think of Earth's hot spots like Yellowstone or Hawaii. They might be spots like this where the ice is especially thin and warm and might contain at the surface water that was not too long ago in that ocean that has erupted up and has not quite been resurfaced yet. But of course, we would like to look ahead to a time where we could actually land on Europa. So concept mission, no selected mission, but concept mission, next step after we get the maps from Europa Clipper would be to plan a lander mission. This is extremely challenging because Jupiter puts out a lot of radiation, which is not great for spacecraft, but it hasn't been anything so far that we haven't figured out how to manage. So this is something that's probably not coming even this decade, but looking ahead maybe to the next decade. And of course, the next logical step would be to actually go into the ocean. And that is already being worked on. We see here the sub-ice submarine ice fin. This is a Earth mission that is led by Dr. Brittany Schmidt, who has recently become a professor at Cornell. She is down in Antarctica right now for the summer test that they do of this. It goes underneath the ice in the sea in Antarctica under the ice shelf, and it's an autonomous submersible explorer. So like a Mars rover, it has to be able to navigate itself, take data, and then return with that data. So how do we even get this thing in the ocean? Yeah, we got 6 miles of ice to try and get through. That is tricky, but the best concept so far is to melt our way through, to have a heater on a probe that caused it to melt and sink down, which would then refreeze behind it so that you didn't create an ice volcano. This is not like going ice fishing. The ice is the surface of the world. This is like drilling through the crust of the Earth. So drilling, not so much, but maybe we could melt through. Now, there is not the only ocean world in Europa. We have found other kinds of deep sea environments. This is one where we consider them to be white smokers instead of black smokers. This is the Lost City is the name of this. If you'd like to know more about this, this is the one that's James Cameron made a video, Aliens of the Deep. I know that this one is currently on Disney Plus. So if you have that, you can go and watch it. We think this is similar to an ocean underneath another moon, Saturn's moon, Enceladus. We know that this one has an ocean because it's spraying it out into space out of cracks in its south pole. This is convenient because unlike Europa's ocean, we were actually able to fly the Cassini spacecraft through those plumes and directly measure what that ocean spray was like. And lo and behold, it in fact was a salty ocean with lots of organic compounds. So the environment and the necessary ingredients for life. Does it have life though? Unfortunately, we do not have any planned missions to return to Enceladus, but there are several concept and proposed missions to return to Enceladus. So this is kind of a stay tuned. We are certainly going back. Japan has even come up with the idea to not just go visit Enceladus, but fly through the plumes, collect information, and then sample return that back to Earth. That is pretty ambitious because we have never brought back samples from anything in the outer solar system. So, but I hope they continue with that. But that leads us to the whole life as we don't know it question and Saturn's largest moon, Titan, which is the only moon with a substantial atmosphere. In fact, so thick that we can't see the surface in visible light. But when you do go to the surface, you see things like channels that are carved by rivers. You see a surface covered in this orange organic gunk, basically similar to the tholins that Sagan was creating in his lab when he was trying to figure out how life gets started, and hosts huge lakes and seas, not of liquid water. The surface here is made of water, ice, but this is liquid methane because it's negative 300 degrees on the surface of Titan. But methane exists in the same form that water does. It's at the triple point. It can form clouds and rain and flow on the surface in liquid. And water behaves like rock because it's so cold that water ice is solid and has a lot of the same properties of solid rock here on Earth. We also think that Titan's atmosphere is actually pretty similar to the atmosphere that Earth started with. The only difference, of course, being that Titan was smaller and in the outer solar system. So this might even be somewhat similar to Earth if you took Earth and put it in the deep freezer and preserved it and didn't let it evolve in the way that Earth did. And those liquid methane seas have led us to ponder, could there be life that instead of needing liquid water, which is our current hypothesis, that just needs a liquid, and liquid methane could work as well? Now, this is still an open debate. There are some biologists that are like, yeah, no way. Liquid methane is very different from liquid water, and we can't think of any way that life could work with methane because of the way the molecule behaves. Others say, hey, we don't know, which is a valid point as well. So we are going to be going back. We don't have any immediate plans to explore the lakes, but we are going back to explore with Dragonfly, which is not just a lander, it's also a drone, because Titan's atmosphere is 4 times the thickness of Earth's and the gravity is 7 times less, making Titan the easiest place to fly in the solar system. So we're sending a car-sized drone to fly around on Titan and explore those organic compounds that are on the surface and to see if we can't figure out what the history of Titan actually is. And we're going to land that craft near a crater because the crater could be a place where the impact was strong enough to melt the surface ice into liquid water. And you would have hot liquid water in contact with all those organic chemicals for a certain amount of time. And who knows what kind of interesting organic chemistry could have happened at those craters. So this is the first place I'm going to pause and stop sharing for a moment. And I want to take any questions that may have popped up about this portion, the idea of looking for any kind of life, which is a pretty close to home search right now, because we actually have several places right here in the solar system we think would be good to look. Before I jump on to that question of technologically advanced alien life that we would be, communicating or visiting with. So questions on this first portion?
Folks, you can unmute yourself if you want to ask a question.
Oh, and Ted, thanks for finding the links to those videos. Oh, hi from Philadelphia. How much radiation can life withstand? That's a very good question. We know how much humans can withstand, and it is a concern of sending humans to, say, the moon and Mars, in that you don't get the protection that we have here on Earth of, 1, a nice atmosphere, and 2, the magnetic field that protects Earth. But we know that humans can withstand a certain amount. Animals, though, there are animals that are far hardier than humans when it comes to many things. A classic example that is used that I think, yes, one of my favorite animals is the tardigrade or water bear. These are little microscopic critters that if you've ever watched Avatar: The Last Airbender, they kind of look like Appa, which makes me love them more. But they actually can exist in space. They can be frozen solid. They can be completely dried out. They can be irradiated. And yet then if you give them their environment, they're happy and back, they reanimate, and they weren't dead. They were just like dormant. So we know that there are forms of life that are extremely resilient to even environments that we would think of. Obviously, those water bears cannot be active and reproduce in those environments, but the fact is they can survive them until they get to an environment where they can become active. So I'm not sure we have a firm number on life in general, which again begs the question of, we cannot rule someplace out just because it's high radiation. And when it comes to Jupiter's high radiation, that same high radiation on the surface of Europa might actually cause chemical reactions that make their way down into the ocean that help it be more habitable. So yeah, we're not sure what that means for habitability. How would we know that any life we found in the solar system is not of Earth origin? Ooh, yes, the question of the concept of panspermia. So this is the idea that we know that planets and other bodies exchange materials. We obviously have found many meteorites coming from asteroids, but we also have confirmed Moon and Mars meteorites that we have found here on Earth, and we have found Earth meteorites on the moon. In fact, the oldest known Earth rock ever found was found on the moon in a rock brought back by the Apollo astronauts. So we know that rocks can be exchanged through impacts, which begs the question, if we know rocks can travel from one planet to another, and we know that there are life forms that can survive in space indefinitely, could that mean that life could spread? Any life we would find is someplace like Mars or Venus. I think unless it were just so vastly different from Earth life, we would always have that question. For instance, if we were to find life that seemed to use the same kind of DNA that we used, I think we'd really be like, yeah, is it just that two different times that chemical reaction happened? Or is this really a case of Earth life? When it comes to those outer solar system moons, not only are they so far away from Earth, but also the habitable environment is underneath the surface. It's inside the moon. We think that finding life there would be almost certainly a separate genesis of life, that would not be a transference of Earth life because of the distance and the isolation of the environment. There is also the idea that it's possible that we're not even of Earth. Mars was possibly habitable before Earth was, and life that we know could have started on Mars and transferred to Earth, flourished on Earth, and died out on Mars. We cannot rule that as a possibility that we might all actually be Martians. But yes, panspermia is a thing, and I think that's why we'd be very interested in finding life inside moons of the outer solar system, because that would definitely say, without a doubt, that life can happen more than once. Could life evolved in a methane environment be more resilient to the level of radiation emitted by Jupiter? So it's an interesting question. Again, the methane lakes are around Saturn, but yes, we have no idea what that life might be like. We have come up with some ideas of, say, how you would create a cell membrane that would work in liquid methane, maybe even what kind of genetic molecule would work in that environment. As to anything else, you're going on pure speculation. So we don't even have a good model of a full organism that could live in liquid methane. So we really cannot say anything about what it could possibly survive. But as I said, there is the idea that on Earth, every time we think there's an inhabitable environment, we go and we find that life has adapted to it and lives in it. So we're now like, can we find anywhere on Earth where there isn't life? And the answer seems to be no. So our boundaries of what life can adapt to are ever expanding. And it's also important to think of, there's a difference between a habitable environment, as in an environment in which life as we know it can be thriving currently, and the environment needed for life to start in. Those are two different things. The environment in which Earth life started in may no longer exist on Earth. If it was the deep ocean, that might be sort of similar, but the Earth has gone such drastic changes that there is a difference between what we consider a habitable environment today based on life that's today on Earth versus an environment needed for life to arise in. So when we're looking out at, say, Europa, and we say the ocean in Europa looks very similar to the ocean in Earth, that's the ocean in Earth now. And so it might be an exact carbon copy of it, but if it's been that way for 4 billion years, it might never have had the necessary environment for life to start in. So you've got to remember that, yeah, Earth has not always been like this. We've got one more, and then we'll go to our second part of our talk. Is evolution a law of nature rather than a characteristic of life? So evolution, in the definition I gave, is a property specifically of life. We sometimes talk about environments evolving, and so that is a word that can be used broadly to mean anything that changes over time and perhaps becomes better over time, better suited. But biological evolution, what we call Darwinian evolution, is a property we consider specific to life because it's directly related to the idea of genetic information, the idea that when offspring are created, when copies are created, that there are mistakes, and that creates variety, which creates, you know, better or worse suited to the current environment. And then as that environment changes, that variety continues, and what is suitable might change. So evolution is used as a word in the English language to include a lot of things, but specifically Darwinian evolution is a biological process, which is why if we saw that happening, we would consider, is that something that's alive, if it met all of those other criteria. All right. Okay, I have to look at this one because I just glanced over it and I saw Star Trek and Asimov. So I'm like, okay, wait, no, I have to see what's said here. Any possibility of silicon-based life? Yes, silicon-based life is something that, yes, you're right. Asimov has talked about, Star Trek has talked about. There was even a comedy movie with David Duchovny called Evolution, where it was considered. Yeah, the point here is that silicon is similar to carbon in many ways. If you look at a periodic table of elements, it's directly underneath carbon. So it's like a heavier version of carbon with a lot of the same chemical properties. Now, carbon is a more abundant substance in the universe than silicon, but silicon is also, silicon and oxygen are what most of Earth's surface is actually made of. So yeah, we cannot rule out the possibility of silicon-based life. And I love when science fiction actually does its homework and is actual fiction based on science. And that is one of those that, yes, they've done their homework and it is something to entertain the possibility of. So yeah, we don't even know that we're necessarily looking for carbon-based life. So life as we know it, carbon-based life, these are all qualifiers that admit that ultimately with only one data point, there's very little, in fact, maybe nothing intelligent we can say about what life actually is. All right, so I'm going to go ahead and I'm going to have to switch here to a different. All right, hold on. Where are you? I've got to find where my screen is. I've got to end this show, and then I've got to bring this one up and start this show. I maybe should have made these all together as one to avoid this, but there it is. Now I should be able to do that. Okay, so now we get to the part where we're going to talk about the idea of interacting with or simply being aware of alien life that can communicate, that can create technology. And this is where we get into the like, hey, if they're out there, why haven't we seen them? Why haven't we heard from them? And inevitably, this brings up the issue of UFOs. And I'm happy to talk more about that, though I have to admit, I'm not very knowledgeable about that, other than to say that UFOs are real. Shocker, they are, because UFO simply says unidentified flying object. There are certainly lots of things that we see flying and we don't know what they are. So that's real. Whether that's aliens or not is again one of those that's the extraordinary claims require extraordinary evidence. Simply seeing something in the sky floating around that we don't know right away what it is, doesn't mean that what you should jump to as an explanation is aliens, because that is such a leap that we would need something far more substantive in the way of evidence for that. At least with any past UFOs, give it decades long enough. If you think back to like Roswell, it was eventually revealed that everything that people saw was actually military experiments. And the military actually didn't do a whole lot to try to convince people it wasn't aliens, because they honestly would rather people think it's aliens than actually look into what the military was doing. Which I'm like, hey, good security technique right there. So with the recent release of all of these things, of new footage of UFOs, yes, I think it's really fascinating. And I definitely see like, yeah, I'm not sure what could explain that, but we've also found a lot of weird stuff in nature. So it's not where my brain goes immediately. I start thinking, okay, what weird atmospheric phenomenon could this be? But I also, can I say it's not aliens? No, I can't. So there it is. But let's think about this. One of the most famous thought experiments is the Fermi Paradox. And so this was developed by Enrico Fermi, who was a nuclear physicist. And the story goes, there's no official record of this because it happened apparently back in 1950 over a lunchtime conversation with some other physicists. But he came up with this paradox. He let down a series of logical steps that led to something that would seem to indicate that there could not be other alien life out there. So let's look at his argument. His first point is that there are billions of stars in the Milky Way similar to the sun. Yes, I'll give him this one. In fact, there's hundreds of billions of stars in the Milky Way, and we actually now don't think that you have to be like the sun in order to have life. We think that you can have stars of other varieties. And in fact, most stars in the galaxy are smaller than the sun. The smaller stars are actually the more populous. Yeah, I'm going to say even more that you can have life around other kinds of stars. So I'll thumbs up on this one. His next argument, with the high probability, some of these stars have Earth-like planets in a habitable zone around the sun. This is great because he said this in 1950, and it wasn't until 1992 that we confirmed the discovery of a planet around another star. So that's that. He already knew. And here's the thing, that wasn't a big shocker, I think, to a lot of us that there are planets around other stars. I think it was just very gratifying to finally have evidence of that. And it was amazing that we'd actually got to a point where we could technologically detect that. So he's definitely right on this. We have found many what appear to be Earth-like planets that are in stars' habitable zones. In fact, we now know that pretty much any star in the sky has a good chance of having at least one planet. So planets are actually commonplace. Many of these stars, and hence their planets, are much older than the sun. If the Earth is typical, some have developed intelligent life long ago. I'm also going to give him this one in that smaller stars live longer. So the sun was not born at the start of the galaxy. So yes, most of the stars in the galaxy are older than the sun. So I'm also going to give him this point. Some of these civilizations may have developed interstellar travel, a step humans are investigating now. Okay, in 1950, he said that. 70 years later, we are still nowhere near the idea of interstellar travel, especially for something like human spaceflight. We are trying to come up with a way to send a micro spacecraft at 10% the speed of light so that it could get to the next star over in a few years versus our current like Voyager 1 speed of 70,000 years. So I don't think we're advanced toward this as fast as I think he was optimistically hoping that we would. So I don't know, and this is not something I think we can take that, oh yeah, any civilization given enough time would develop interstellar travel. There are some things that just might not be realistic. And understanding the vast distances between things, this might not ever be a thing. Communication, perhaps, but travel, I don't know. Might be rare enough that it hasn't happened in our galaxy. So I'm going to disagree with him on this point. Even at the slow pace of currently envisioned interstellar travel, the Milky Way galaxy could be completely traversed in a few million years. No, I'm again going to severely say a big no to this. The Milky Way galaxy is 100,000 light years across. So that means even if you could travel at close to the speed of light, hold on. All right, can everyone hear me? Let's try there. Can everyone hear me now? I was on my AirPods, but they appear to have died. So, all right, I should be on my computer, microphone, and speakers. So let me go to the chat. Yes, excellent. Okay, yeah, that's what happened. All right, so in this case, I'm going to say absolutely not, because even at close to the speed of light, as I said, it takes 100,000 years just to go in a straight line from one end of the galaxy to the other. But of course, the galaxy is a three-dimensional object. It's a disk so it's circular and with a thickness. It's like a pancake. I would not say if you traveled from one side straight line across to the other side of a pancake that you had traversed the whole pancake. And so even at the speed of light, saying that you would have explored every little corner of the galaxy, I don't think that's going to happen in just a few million years. So I think there's a big difference between simply going from one end of the galaxy to the other and traversing the galaxy. So I'm going to say big no on this one.
And since many of the stars similar to the sun are billions of years older, Earth should have already been visited by extraterrestrial civilizations, or at least their probes. Even if I could give him everything before this, I'll give him this point. But let's think about it. Humans have only been at a point where we would even be able to recognize an alien probe for what it is. For what? A century, a few centuries, maybe not even 100 years. The Earth's been around for 4.5 billion years. Alien probes could have landed here, but maybe it was back in the time of the dinosaurs, and since then there's zero evidence that remains. So the statistical chances that in just the last, say, 100 years, where we might have recognized something as an alien probe, yeah, that's a tiny blip in the whole history of the Earth. And unless they're sending probes out like clowns coming out of a car, the chances that one of their random probes would actually land on Earth in this little window of time that we've had so far where we would recognize what it is really inconceivably a small chance. So based on all this, though, Fermi concluded that, well, since that hasn't happened, I guess there's no intelligent life out there, at least not in the Milky Way galaxy. I hope that I have offered a lot of counter arguments to what he said. And so these are all reasons why we should not just take the Fermi paradox as evidence. And there's also a very famous saying, of course, that absence of evidence is not evidence of absence. So just because you don't find evidence of something does not mean you can firmly conclude that it doesn't exist. So who was this guy and what was he talking about? As I said, he was a nuclear physicist. One of the other things he was famous for were what he called his guesstimates. So you might have heard this word. It's somewhere in between an estimate and a guess. So you maybe didn't thoroughly calculate things to get an estimate, but you also didn't just guess off the top of your head. It's the thing that's in between. And these became known as Fermi problems. And the one he really became famous for involved estimating the power of a nuclear bomb based on having been present at least 16 kilometers away from the blast site during a test. He managed to, just using what he had on hand and his rough knowledge in his head of things, estimate the power of the bomb to within a factor of 2. And that might seem like, well, he's off by a factor of 2. We're talking in a thing of powers of 10, orders of magnitude. Whether a bomb is 10 kilotons or 100 kilotons is a much more significant question than is it 10 or 20. His guesstimate on it was 10 kilotons. It was actually a 20 kiloton bomb. This kind of made the military a little nervous because they're like, if this guy just standing there with nothing but his body, his brain, and a piece of paper, could that accurately estimate the strength of our bomb? A spy could do that too. And this is one of the reasons they started testing underground. So it's a good thing that he shared with them that, yeah, you don't really need a lot of complex calculations to get a good enough answer to a question like this. So now I want us to take just a minute and try our own Fermi problem. You have your option. You don't have to play along at all. Or if you want to do just the total guess off the top of your head, free to do that. Or if you actually want to try and do a rough calculation in your head to see if you can come up with a guesstimate on this, everyone can play in any way that they wish. And I would encourage everyone to use the chat for this, to just plop your numbers into the chat when you think you have an answer that works for you. Here's the question. How many high schools are there in the US? And this is one of those where your first reaction might mean, well, I'd have to go Google that. No. I want you to try and use just the common knowledge that you have and see if you can work out at least a rough idea of what that is. And we're thinking order of magnitude here. Is it 10, 100, 1,000, 10,000, 100,000, a million? Like, we're looking for that kind of level, or even a little more accurate. So I'm going to go ahead and I'm going to set my timer for 1 minute. It's going to seem like a really long time because it always does when you're just sitting here doing nothing. But again, yeah, if you want to just pop off of guess off the top of your head, go right ahead. If you actually want to sit there and see if you can calculate it, a calculator would be allowed, though. If you want to do it in your head, that's kind of fun, but no Google search. I wish I had the Jeopardy music going on right now. 42, no matter what the question is. No, only if the question is the ultimate question. And what's the answer to the ultimate question of life, the universe, and everything? If you've never read Hitchhiker's Guide to the Galaxy, go read that, because that's what we're joking about, and it's marvelous. I've probably read that book more times than any other book. So I see 10,000. Someone's giving that. Okay, 100,000. People are giving out order of magnitude. Good. All right, 7,500. Okay, 1 million. 2,000 per state averaged. Okay, so times 50 states. You're proposing about 100,000. Okay, 200,000, 5,000. I think that no comp, 300,000, 16,000, 35,000. Yes, there was a movie. I try not to think about it. I did not care for the movie. I'm going to say that. Had some good points, but just, you know, when you've read something over and over again, you've pictured it in your head a certain way. Yeah. It also left out some of my favorite parts. So, ooh, an exact estimate, 26,726. Okay. Oh, yes. Alan Rickman is awesome no matter what he did. Okay. We'll all agree on that. All right. And that is a minute. All right, so let's see how we did here. So here's an example of a thought process you might have gone through. About 300 million people in the US. It's actually closer to 330, but again, we're order of magnitude. So rounding to like one significant digit and a bunch of zeros is great for doing this in your head. Since people live around 80 years, they spend 4 years in high school on average. So we're talking about a 20th of your life is spent in high school. So 300 million divided by 20, we estimate there are currently about 15 million people in high school at any given time. Let's assume an average school size of 1,000 people. Obviously, that one comes in a huge range. There are schools that are larger than that. There's schools that are much smaller than that, but let's just go with that. Number of high schools, therefore, is 15 million divided by 1,000 or 15,000. So this is a guesstimate. So what's the actual number? About 24,000. So you can see that, yeah, in everyday life, you might think there's a big difference between 15,000 and 24,000. But when it comes to answering a question like that, it's actually pretty impressive. And there are a lot of these out there. A fun one that requires a little bit of research that I've done with kids is, what's the best way to evacuate New York City in the event of a zombie apocalypse? By boat, by plane, or by car? That one, yeah, you kind of have to look into, you know, how many airports, how many bridges, and how many ports. But it's also an interesting thing of asking, like, if you had to do one of those and only one of those, which one would evacuate the city fastest? So this is the kind of thing that we want our brain thinking of when we come to the next famous physicist who tackled the alien problem, Frank Drake. So Drake came up with something called the Drake equation, which is essentially a Fermi problem. And this idea that maybe we can get an estimate of the number of technologically advanced civilizations in the galaxy by simply multiplying a series of numbers together, like we just did for the high school. So the little bit of algebra here, letters standing for numbers. Bear with me though, we're doing nothing more than multiplying. So on one side of the equation, we have n, which is going to stand for the number of technologically advanced civilizations in the Milky Way galaxy. This is what we'd like to guesstimate. So the first thing we have to know, of course, is the rate of star formation in the galaxy. This idea Fermi understood, like, as that you didn't just have a galaxy born with all the stars in it was ever going to have. Stars are constantly being formed. So we need to know what that process does. Next, we have to think what fraction of those stars have planets. Then we have to think of what fraction of the planets actually are suitable for life. Then we have to think about how many of the planets suitable for life actually get life. And then out of those, how many actually get up to intelligent life? And of those, how many of those intelligent life get up to technological advances that would be detectable, if not actually having a conversation in traveling to, but just knowing the existence of, And then the last one that's kind of a bummer, nothing lasts forever. How long does an average technologically advanced civilization actually stick around? Because yeah, maybe a bunch have existed in the Milky Way, but if they don't last very long, none of them might be coinciding with us right now. So this is the question again of now. How many are there right this moment? Not how many have there ever been? How many are there now that therefore we could detect, communicate, or even have travel to us? So that's the equation. Let's now take it step by step, a little more algebra. We're going to give this a try. So we have all of our values lined up there. So let's talk about what we know and don't know. The order of these kind of follows the order of our knowledge. Rate of star formation, we actually know that number very well by now. It's about 1 star per year. Fraction with planets. This also was something that when Drake came up with this, the first one was the only one we had any solid evidence on. We now, as I said, know that planets are extremely common, and we can actually kind of round this up to 1 because the question really seems like, do any stars not have planets? So we'll go ahead and throw that in as a 1. This is also one that was only recently we even have any idea what this is. Based on the data we have, it appears we've found thousands of planets, about 40% have an Earth-like planet in the habitable zone. After this, folks, this is where the guess comes in. We have no firm evidence for anything in this equation beyond those 3 numbers, which means now is the time where you just get to have fun and play around with sticking in numbers to see what you get. So this is my attempt. This is when I did it. All right, we know that one. We know that one and that one. All right, where did I go from here? I'm going to say that every time a planet is suitable, life arises. I'm being extremely optimistic here, I realize, but I'm going to go ahead and play at that life is something that just happens the minute everything is in place for it to happen. So every planet that's habitable gets life, some form of life, any form of life, the first part of our talk. How often does that life develop into intelligent life? I came up with this small number of 2.5%. Let me explain where I got that number from. Humans are not the only intelligent life on the planet, so I acknowledge that. Like, we now know that intelligence comes in many forms. We have other apes, we have porpoises and whales, we have birds. Intelligence is all over the place. So how did I get this number? The central nervous system evolved about 500 million years ago, and we had dinosaurs, which definitely we see evidence that some of them had intelligence 250 million years ago. So I'm going to say, like, intelligence to the level of being able to do technology maybe has existed for about 100 million years on our planet, and life began at least 4 billion years ago. So that is where the fraction is coming from. So I'm thinking of it, and the entire time there's been life on Earth, how much of that has highly intelligent life on scale with human intelligence existed. So I'm giving that a maybe pessimistic 2.5%. All right, how many of those get up to a level that would be considered civilizations, technologically advanced civilizations? Okay, now I put lots of question marks under it because I have nothing to base this on whatsoever. So I'm going to throw out 10%. Let's say 10% actually progress to technology. And then how long do they last? I don't know whether you think this is optimistic or pessimistic, but I went ahead and just threw in 2,000 years. Like, okay, 2,000 years, you get existence at that level of technology. So what does this all lead to? If you multiply all this together, I conclude that there are 2 civilizations technologically advanced enough to be detectable in the galaxy now, and we're one of those. So by these calculations, there's only one right now other civilization as advanced or more advanced than us. This is kind of a downer, I think, if you were hoping for like this network like you see in Star Trek. But again, a lot of those numbers were purely like just out of thin air. So you can come up with your own and see what kind of answers you get. Now, scientists have done this yeah, there's a lot of these numbers we don't know, but what we can do is run something called a Monte Carlo simulation, named after the casinos there, where you run thousands or even tens of thousands, hundreds of thousands, millions of times with random values for these numbers and come up with this statistical picture of, if everything's equal chance, what does that look like? And it turns out that in about 30% of the cases, you end up with n less than 1. And of course, we know there's at least one, there's us. So this also is a bit of deflating if you were hoping for aliens, and the fact that, yeah, they might, we're not saying they can't be like all over the place like in Star Trek, but it does not seem like that would be the case based on what we do know in the Drake equation and, you know, what these simulations show. Now, these simulations assume that all things are equally likely, and that's obviously not the case. This is about having a fun thought experiment and seeing, when you tweak those numbers, how that affects the answer overall. And so this is where I would like to, you know, we went a little over. This is where I'd like to stop and take more questions at this point. And I think, yes, traverse definition equals travel across or through. And so, yes, I think that, yeah, it depends on, you know, if he's talking about traverse in that traveling from one end to the other, yeah, I'm fine with that. But if he's using that to conclude that you would have explored the whole galaxy and been able to rule out, in other words, he's making the argument that since they've traveled the whole galaxy, they would have found us. And if you just went from one end of the galaxy to the other, the chances that that line would intersect us are so close to 0 that it's not an argument. So yeah, even if that's what if that's indeed what he meant by traverse, I still don't think that it's a good argument. And again, it's a moment of debate. I love this whole, like, let's debate what it is. And of course, like I said, there's no official record of what was actually said about the paradox, because it was literally a lunchtime conversation that I think someone scribbled down notes from after it happened. So I see that a lot of you actually got really good order of magnitude estimates on the high school question. Well done. Ah, yes, source, it's National Center for Education and Statistics, 24,000. Always good to put your sources. So I encourage everyone to go play around with Drake's equation at some point and see like what kind of different scenarios you can come up with that and what that means for how prevalent technologically advanced civilizations could be in the galaxy. I did not entertain other galaxies because those are so far apart that we can't conceive of traveling, even detecting across those distances. So say, considering Murphy's law, if life can happen, it will happen. This is where, that's why I threw in 100% for if it's habitable, life happens, because, you know, you have that concept that Feynman, physicist Richard Feynman came up with, where he was like, quantum physics seems to suggest that anything that's not forbidden is mandatory. This idea of if it can happen, it does happen. And if the universe is in fact infinite, then that is definitely fact. Anything that can happen has happened. But again, if we're just limiting ourselves to the little galactic corner that we're in, that becomes, okay, is there scientific prime directive, if you will, about our course of action if we do find life on another world, as in, will we try to go and intervene or leave our own DNA behind on that world? I think it's an excellent question. I've always been fascinated by the idea of the prime directive in Star Trek. I do think that we would need to come up with that. And the problem is the same with detecting any life. We still do not have like a good international agreement on planetary protection, the idea of not contaminating other worlds and what we would do if we detected alien life. How would we both protect it and protect us from it? In fact, there was just recently a letter, an article written in Nature about the whole, like, how do we proceed if these samples come back from Mars and there's microbes in them? not just how do we detect that, but how do we make sure that that doesn't contaminate Earth, or that it's not an Earth contaminant? And so this is where you're going to have to come together as a planet and try and figure out how we're going to approach this. And then you have the question of, if the scientists do agree that they've detected alien life, how do we go about disseminating that knowledge? Like, what is the procedure and the ramifications? And this is where, again, I highly recommend, you know, both the book and the movie, Either or Contact, Carl Sagan's, was made into a movie in the 90s with Jodie Foster and Matthew McConaughey. It takes an amazing look at the fallout and the process of, if we did find life, what would be the implications? Another alien movie that I highly recommend is Arrival. I loved that one because Contact made the approach of, like, the universal language is mathematics, and we should always be able to talk to any other alien civilization if we speak math. And on one hand, I tended to agree with that. And then I saw the movie Arrival, and it really kind of points out the fallacy of that. And as someone who exists with a lot of family members that are language experts, that was a very interesting perspective to come at things with the idea of linguistics. So I also highly recommend that movie as well. The movie is Arrival. Even with the Drake and Fermi, probably more intelligent civilizations in the universe than high schools in the US. Yeah, when you get down, you could take a step back, you could take away the how long does it last, you could take away the technological advancement and just get to, like, intelligent life, because we've certainly seen that we now accept intelligent life on Earth is not just limited to humans, but humans are the only ones that have built radio telescopes and spaceships. We do know that other animals use tools. We now recognize that we used to think that defined us. It actually doesn't. And there's even a species, I think, of monkey that they're like, if you're objective, they've entered the Stone Age. Like, if you really look at them the same way we look at anthropology. And so it again is the idea of what percentage. I think I put 10% for that. Maybe that's way higher or way smaller. I imagine that intelligent life is actually, yes, pretty common, but how does it get to technology? Not every intelligence will prioritize technology necessarily. And even among those who do, how many stick around long enough to get to a level that interstellar travel, communication, detectability would be there? All very excellent questions. All right, well, I want to thank you all again for having me, and I look forward to doing more talks with Danby, and hopefully anticipate coming back to the in-person ones, which would be awesome. And oh wait, there's one more question. I wonder if any civilization could skip the radio phase altogether. This has been proposed. Like, we've made certain assumptions about radio communication and even what frequencies that would make logical sense. But recently people have begun to wonder, what if they're not using radio? What if they're using a form of, like, laser or visible light instead, or using some other form of communication? Generally, up until just a few years ago, our only way of having knowledge of the rest of the universe was light. Literally, we had one tool. Now, light comes in all sorts of wavelengths, but we had one tool for the entire history of astronomy for studying the universe. And then we finally detected gravitational waves. And that was significant because for the first time in human history, we had a second tool for exploring the universe. We went from 1 to 2. Perhaps they would find a way to communicate using gravitational waves, or something that we still haven't yet figured out how to detect. So again, when it comes to life, we are making tons of assumptions. The Drake equation has tons of assumptions. How we go about trying to detect life elsewhere in the solar system has tons of assumptions of where should we be looking. So open debate, definitely. All right, well, I'll hand it back to Ted, and I'll thank you all again for wonderful questions, and hope all of you had a pleasant evening.
Yeah, I think we should all give a big round of thanks to Zoe. I don't know how many of you have your audio on, but you could go, thank you. We very much enjoy these presentations. It actually gives us something important to think about I'm looking out the window here, on a very gray and otherwise boring Sunday afternoon. But even if it was bright sunshine out there, I'd be here listening. So thank you very much. And thank you everyone who has joined us today. The recording from this live stream, from this talk, will be on YouTube, and you can always go to danbycc.org and find, let's see, there it is. Go to danbycc.org and find the recordings of these presentations. So once again, thank you very much, Zoe, and thank you everyone for attending our presentation. Thank you. Thank you.